And yes, it is so awesome to have Karen Connors joining us today. And so Karen has had a varied career across mineral and petroleum exploration. She specialises in regional synthesis projects and integrated interpretation of seismic with potential field data to understand 3D crustal architecture. She's currently a principal geologist in global target generation at AngloGold Ashanti, as well as an adjunct professor at UQ. And it is going to be totally awesome hearing from her today about crustal architecture and evolution of the North Australian Craton. So please have a great time. Keep using the chat. We'll open up the floor at the end. And yes, thank you so much, Karen, for joining. It's amazing having you here.
Excellent. Thanks very much. Well, thanks, everybody, and I appreciate your time today. I do want to first acknowledge co-authors from this work. Over the last few years, I've done a lot of work with Janelle Simpson and Don Brown at GSQ, and then as well Lynn Pryor and Jay Blevin I worked with at FrogTech for over a decade, and have been we've gotten together recently to pull together some of the work I'll show you as we go through the talk. There we go. Just get myself all set up. So as I mentioned, I was at University of Queensland Sustainable Minerals Institute when I did this work. So a couple of the overarching thoughts that I'd like to leave you with today. The North Australian Craton, it's obviously quite large. It's a composite crustal entity. Craton is probably not the best name for it, and but it's the well-recognized name, so I'll use that today. Within that, there are a number of really well-defined basement terrains, but some of those terrains are a bit more difficult to define their boundaries really well, and that's in large part due to reworking and the nature of the crust. So we're lucky in a lot of areas, and especially through the NT in Queensland, there's a lot of MT and seismic and tomography, and these data sets help provide some of the key insights. But the fundamental data sets behind this work and the original interpretations were fundamentally just based on the gravity and the magnetic data. The key thing here in the North Australian Craton is you've got a long history. So you've got over 2 billion years where these basement terrains have evolved and continue to control the basin development and then subsequently the shortening and inversion. And understanding the crustal architecture is fundamental to think about those framework studies and then to be able to apply the mineral systems approach for exploration. So I'll hit on a few examples and talk about different deposits, but through this area, I'll especially focus on the implications for lead zinc. My understanding of this region has evolved over almost 15, almost 20 years now, with work at FrogTech, and Geognostics is the company that is now taken over the IP there. And so with the sea-based projects focused on depth of basement, there was a big focus on understanding the underlying basement. So my understanding comes from my work there at FrogTech, and that built on the work of a lot of colleagues who were there even before I joined in 2006. Lynn and Jane, as I mentioned, are co-authors, but there's a host of other colleagues there. The last few years have been at Sustainable Minerals Institute, and I've been much more focused on integrating the deep crustal seismic with the gravity, MT, and other data sets, and working closely with Janelle and Dom on that. So just an overall image so you can see the comparison of the North Australian Craton. It's much bigger and more complex than the West Australian or South Australian Cratons. I've just highlighted in pink here a couple of the more competent, more classic definition Cratons within that area. I had a quick count. I have, I think, 37 basement terrains throughout the North Australian Craton. And my interpretation here builds on that from FrogTech, and Geognostics in 2021 released an updated Oz Sea Base, and they included the basement terrains in that. So the interpretation I'm showing you is what I've modified in the North Australian Craton region and building on that work. The key thing to keep in mind here is when I'm talking about the basement terrains, I'm talking about the mid to lower crust, and those are going to be dominantly older than about 2200 MA, and that's coming from the neodymium samarium data. And so we have a host of younger cover basins sitting on top. So this is just showing the chart from the Northern Territory. And we have basins from about 800 to 1400 and then younger. In fact, Neoprote, Mesoprote, Neoprote, Paleozoic sitting on top. But when we're talking about, for a geologist looking at outcrop, crystalline basement, we would describe as rocks that are deformed and metamorphosed. So this package that's roughly 1880 to 1800 is clearly deformed and metamorphosed across much of the North Australian Craton, and there's equivalents coming to the south and east into Queensland. That basement is younger as we go to the south, and where the margin was active for longer. So although these terrains are technically basement rocks, they are still deformed and metamorphosed supercrustal rocks that were deposited on the underlying basement terrain. So fundamentally, we're trying to get back to these Archean and to early Paleoproterozoic blocks that form the base to the North Australian Craton. So I don't want to get into the colors too much, and I won't show this again, but red is just highlighting the large cratons or smaller cratonic blocks. And I've included the core to Mount Isa, and I'll show you that in section in 3D. Undifferentiated continental, we're just not sure, or it's too reworked. But I will talk about interpretation of accreted arcs that I've highlighted here in green. And then in the pinky peachy colors, it's either an accretion complex or an undifferentiated orogenic belt. So it's a belt that's been quite deformed and possibly sediment dominated. So you can see the different colors of the dots and circles here. So that's the neodymium model ages compiled. I forgot to put the reference in by David Champion at Geoscience Australia. So the most of the ages we see are sort of 2600 down to about 2300 or 2200, and you can see all these dark and lighter blue dots, some older Archean ages coming out of the Pine Creek Craton. And then as we come to the east, you can see more of these green dots that are the younger ages, 2300 to 1800. So these are the model ages coming from the granites that outcrop its surface and telling us what we think the age of the underlying crust might be. It was something, oh, yes, that's what I was going to say. So the Archean ages from, we see those extend right out to east of Etheridge. So Georgetown sits about here in the eastern edge of the Etheridge province. So we still see Neo-Archean ages extend right out to this eastern area. Sorry, let me get that pointer on. Make it better. There we go. Now, this is just the outlines. I just want to highlight some of these terrains, and then we'll look at things in detail. So there in red are the more cratonic blocks, so dominantly Archean to early Paleoproterozoic. Let me see. Now my clicker's not working. So this, where I highlighted, I think there's accreted arcs through here. I think this collision, this event had to be early, so probably pre-2200, and we'll look at the data in detail. We have seismic down here. We have the gravity and magnetic data here, so that was an early event. I'm not going to talk about this western area, but the latest ages suggest a 1900 collision in here. The aileron probably rifted a bit, had to be reaccreted by 1870 is the general understanding prior to deposition of the younger sequences. So then from 1870 to 1790, we have a few different things happening. We've got a passive margin here in Halls Creek, west of the Tanami. Interestingly, at the same time, the evidence from the Litchfield terrain up here in Pine Creek suggests it's an active margin, which means we have to have a transform boundary through here. And when I sat down and thought about that, that gave me my best suggestion for the nature of the Urapunga fault zone. There's an interesting fault zone if you've looked at this area, and there's an offset between these, the north-south trending basins and basement terrains. I see this area through Tennant Creek and to the east is a deep rift, and I'll show you that in seismic that formed, say, 1870 to 1790. Kimberley reaccreted 1830 to 1800. And there's a good paper from the UWA group recently looking at this, but we don't know. This collision here on this margin is as old as 1800 or as young as 1300. I would argue it probably came together early, but that's still unclear. So from 1790 to 1590, we have these vast basins forming over much of the North Australian Cratons, MacArthur down through Mount Isa and out to the east, right to Georgetown and Etheridge province. And within that, I see a very broad, deep rift, focused around 1700 to 1620 here in the east. So we'll look at that in the seismic as well. Final, we have the Eisen orogeny and related events from about 1600, and that's the end of the active margin here in Central Australia as well. I'm not going to have time to talk about the Thompson origin, but I see this as being dominantly reworked crust that was part of the North Australian Craton. Now, I've just flagged this little triangle in here. This core, Pitta Pitta and Central Isa, this core to the Mount Isa region. Every time I look in here, that you'll see on some of these images, my terrain boundaries have changed a little bit because I haven't had time to update all the images. I go back and forth between thinking this terrain boundary swings a bit out here, and that gives you a timing relationship with the east-west trending terrains here, which says it's come in and collided probably along with this craton, or does it wrap around the outside? I'm hoping as more of the data, the MT and tomography data, final data sets come out through here, they will help shed some light. Now, I'm going to quickly take you on a cross-section across much of the North Australian Craton along some of these seismic lines here. So this is just a quick overview. We'll look at a lot of these in more detail. So coming from the northeast, we have the Newmal terrain and Abingdon. These were originally described by Russell Korsch and the GA team. A lot of low angle faulting in here. And then we step through, this is the old 94 seismic line, the first one from up at Mount Isa. We have the thicker, more competent crust, and we see the older neodymium ages. And now we're swinging northwest along the Queensland NT border, Altjawara, and Murphy South with Tennant in between. We've stepped to the west. Here's the Murphy South terrain again, and its relationship to the Arnhem Craton here to the north. And this line is based on seismic here in the eastern half, and then I've just extrapolated west to get us across to the Tanami. I have no idea on the constraints and the boundary there. But again, just showing Arnhem, the north-south trending Malapanya terrain, which is not, we're only just getting a dog leg glimpse of it here, and the smaller cratonic blocks beneath the MacArthur and Roper Basin. So I'll come in to start and look at the Pine Creek and Arnhem Cratons and the evidence for this suture, the north-south suture and the east-west suture here, and then we'll look at the Mount Isa and Newmal terrains. Now, this is one of those images that I didn't get around to updating. So it has some older terrain boundaries, but it's all, the terrains are the same, things are just tweaked a bit. So we have Pine Creek and Arnhem. These are large terrains, have a regional extent. They lack a preferred fabric, and you can see the numerous granites, especially in the onshore area where we have high resolution data here in Pine Creek. Arnhem is mostly offshore. We see a similar effect, but the data resolution is much lower. And they're separated by this negative and positive gravity anomaly that I referred to as Milingimbi and Miramina. So this linear terrain separates the larger cratons, and then to the south, again, we've got a paired negative and positive gravity anomaly in the Murphy terrains, and these come along and truncate the bottom of the northern terrains. So when I take that off, and this just highlights why you want to be trying to get the regional satellite data and including the offshore area, which GA has nicely done in the more recent gravity images. You can see how prominent that gravity anomaly is. It extends for 1,000 kilometers up north to coming up to PNG. That is a major structure. So without any seismic data up here, you can say there's got to be a terrain boundary. And that actually comes down and it controls. It's not as well defined onshore. You have some other factors with the overlying basins, but this is essentially controlling the Walker and the Batten fault zones. And of course, you've got Tina and MacArthur River HYC localized and controlled by these basement terrains. Down here with the Murphy terrains, south dipping crustal scale structures. They're now confirmed by the seismic and MT, but originally interpreted just on the gravity and the magnetic data. And we will look again at the seismic that we can see the localization of depot centers, specifically around that Murphy South terrain. So because we've got the strong positive gravity anomaly, we're interpreting a mafic to ultramafic composition. And you start thinking about an accreted arc, some sort of relic suture. Could it be a large intercratonic rift with a lot of mafics like the mid-continental rift in the US? But the fact that you've got the paired negative positive gravity anomaly makes me favor a suture zone, a relic suture, so that the negative anomaly is more of a deformed passive margin, and the positive anomaly an accreted arc. So there's probably closure of a small ocean basin, certainly prior to 2200, and potentially during those really early stages of the evolution of the North Australian Craton, but we don't have any evidence on the timing. So this is key because we're looking at the controls on the basins that host the lead zinc mineralization. So just an overview, this is the sea base image in the background, and this is highlighting the extent of the basically 1680 to 1590 MA units that host the lead zinc. So I've got zinc deposits in green, lead in blue, and also showing the copper. This is from a base metals focused talk. The smaller pale dots are the occurrences. Now, I think there's a big depot center. I think there's clearly a big depot center, and we'll look at this in detail. But it's not shown as a basin here because those rocks are deformed in the eastern fold belt of Mount Isa. Those rocks are deformed and metamorphosed. So in the previous work done through here, it was classified as basement, so it doesn't get flagged as a basin. So we've got this broad basin, at least 1,500 kilometers wide, but within that we have these linear rifts. The Walker Fault Zone, Batten, the Brunette Downs Rift Corridor. You can see we've got a north-south one and east-west one. Mount Isa, we get lost in here, is smaller north-south, and then this broad one to the east. Now, looking at the lab depth model from Hoggard and colleagues at GA, they highlighted the 170-kilometer depth contour of the lab, and were both observed the relationship between that contour and a lot of the mineralization, especially the base metal mineralization. And their model their interpretation of this is that you end up with a thicker rift package due to the increased buoyancy, because you're on the margin of the thick cratonic lithosphere. And that makes the difference in being able to develop a really large or giant deposit. And they suggested that you have to be on the edge of the thick lithosphere to be able to get the largest volume of fluid rock interaction, whereas a smaller deposit can form in any extensional setting. So hopefully I've done that work justice. But and I do agree in general with this, but I think there's a little bit more to the story, because I see a craton, another craton offshore here in the Gulf of Carpentaria. So it surprised me from the start that this contour would come through here. So there is a new data set that's just come out, Delat and others, with a new model. And so this is just looking at the velocity variation, not converted to depth. But you can see it trends more north-south through the Gulf of Carpentaria and extends all the way up to PNG. So the seismic velocity, most of the variation is due to temperature, and that facilitates that conversion to depth that Hoggard and others used. But it also reflects variations in composition water and whether there's any partial melted. Now, the extent and thickness, we can see the extent of the thick cold lithosphere defined by the higher velocity, and it's an area with less reworking and or less refertilization, if you think of the examples from around Olympic Dam. So there's some lateral variation in here, but that thick cratonic lithosphere extends across much of the North Australian Craton and the other cratons. There's an intermediate area here that goes beneath the Thompson origin and Delamerian. You can see the cross sections. You can see, so this is the depth scale. So I've flagged these depth sections at 110 and 150. You can see how sharp that transition is. So I've put my basement terrains over top, and you can see where Arnhem sits here. Now it's interesting, there's the dashed 170 kilometer contour, and you can see there is a zone where the velocity is a little bit lower, not as high, corresponding to this area. So there is a change through there. And I think that's significant, and we'll come back to that in the end. So this area where the lithosphere is thinner here to the east, they interpret it due to cratonic erosion related to the rifting. And I'll show you evidence for the extent of that rifting. And this extension to the east, because their model differed so much, they did some specific testing, and they're confident in this new model. So we'll start here on Mount Isa. So it's hard to try and go through quickly without going through a lot of detail on the stratigraphy. But in general, the basement terrains on all these sections are labeled and generally trying for the pink colors, numerals in green. Leichhardt Super Basin is in a paler green, Calvert in orange, Isa in blue, and then in the east, the Soldiers Cap group, Kurridarla group are in these yellows and greens. Now, I haven't done these cover sequences are widespread, but we haven't done a detailed interpretation of them. But you can't interpret the basement without understanding, how deep your overlying basin is. So this helped us constrain, but it's very much a first pass interpretation of the cover sequences with more focus on the older basement. So the approach here, so there's the 9 regional sections. I can't remember how many line kilometers that we did in this first interpretation, and this is published by GSQ. But it really was the ability, taking the time to do the integrated interpretation of all the seismic lines and the other data set that allowed us to come up with this model. Because if you look at one individual line, not every feature or terrain boundary is well defined on a given line. But when you interpret everything together, you can extrapolate that. So the scale on all the seismic lines, I've got red lines there showing 5 seconds two-way time, and that's essentially a factor of 3 for a quick depth conversion. So all these sections go down to about 60 kilometers depth. You can see, so this is the Kalkadoon-Leichhardt belt. So that depth goes down to about 6 seconds here. So that's based on the gravity model, just showing the overall extent of that body rather than a seismic interpretation. So the other feature in plan view, because it gets hard when you're going from plan view to section to try and show these 3D terrain boundaries in plan view. So red shows where the Gidja structure projects to its surface, which is well east of the end of this M6 seismic line. But the key feature, when you're just thinking about the basement terrains, the boundary between the two basement terrains is about 100 kilometers further west, because this boundary dips so gently, sort of 25, 30 degrees. So I show in red the near surface terrain boundaries, and the ones you see in gray are further at depth, say getting down to mid-crustal levels below the cover basins. Jumping down to the CF3 line here across the southern part of the Mount Isa province. Pita Pita is an elongate north-south trapezoidal block. It's higher density and it is more resistant. We can see from the MT data. You can see this east dipping boundary with this more tabular overlying central Isa terrain. It's quite a thick tabular block. This boundary we refer to as the Urandangi-Burketown fault zone and extends a long way north-south along that western boundary. So central Isa, is it a deformed margin or is it was it originally a distinct terrain? It's hard to say. At surface, as you get up into the main part of Mount Isa, you have the extensive outcrop of the Kalkadoon suite and then rare older gneisses in outcrop, but we don't get any good sense of those. Now, I think there's some clear control on the post-1780 cover basin. So we've got the southern extension of the Leichhardt River fault trough here in the west, and I think that's controlled fundamentally by the reactivation of that terrain boundary. And you can see the Leichhardt superbasin here in the east. The seismic is the consistent dip on the seismic is quite good here. So we know we have a thick package. It's more extensive and thicker there in the east than in the west. So now I'm showing M6 and CF3, and the geometry is remarkably similar. These seismic lines are 100 kilometers apart. So that similarity helps you interpret undercover through these areas. Pardon me. So we have the resistive Archean, dominantly Archean cratonic block of Pita Pita. We see a reworked margin of the adjacent Ulchawara terrain, which is a more cratonic block as well. Central Isa is going to be Archean Paleoproterozoic, and Numal is more dominantly Paleoproterozoic. There are no Archean ages from in there at the moment. And Abingdon, as I indicated, as you go further east, there is still clear Archean crust in there. Now, the cover basins, as I highlighted, we can see on both these seismic lines how much more extensive the Leichhardt superbasin is in the east. And that's contrary to what you see when you're looking at the plan view maps. It's controlled in part by the Gidja structure, and likewise that feature controls the overlying Soldiers Cap Group, Kurridala Group basin that extends well to the east. So 3D summary. This is just in leapfrog, so the images are projected onto the seismic lines or draped onto the seismic lines, just for a 3D overview. So we're looking to the north along the core of Mount Isa, there, Central Isa and Pita Pita. There's the Urandangi-Burketown fault zone near surface. And as I highlighted, the difference between the surface and mid-crustal depth of those structures. So I see three distinct numal terrains, and we'll look at this in a better image in a moment. But the key feature is that the strong west-dipping fault blocks and fabric of numal east correlates quite well with the numal terrain that we see to the south on the CF3, M6, M5 lines. So we don't necessarily see the numal west and central terrains extending to the south. Now the MT data, so this is from Jiang et al., 2019, gives us some insights. This is the M6 line sitting in here with the 3D image of the other MT lines. But the key feature is that we've got such a good match. You put the seismic main boundaries on top of that, and you just get a much better picture of what's going on in the crust. So we have resistive pitta-pitta. We see the conductive features associated with east-dipping structures in the basement in central Isa, also in the cover sequence here below Osborne, associated with the east-dipping structures. Numal, we have a more moderate conductive anomaly associated with the numal terrain, which distinguishes it from pitta-pitta to the west. We can also see that there appears to be a relationship between the MT response and the steep structures of Pilgrim and Cloncurry faults. So looking at this, and I will come back to this point where I can explain it a little bit better. I think the low angle structures dominantly accommodated the earliest stages of shortening, and then the steep structures during the later stage of the shortening and transpression. So we have both these steep and moderately dipping structures that we see in the seismic and the MT. And when you're thinking about your crustal architecture and your first order and second, third order fluid structures. Based on what we know about the Williams granites, the depth of the source corresponds well with the top of the numal terrain here. So co-location of MT and seismic, I think, is really key and well worth doing. It provides a lot more insight. Okay, we'll jump in and look at numal in a bit more detail. So we looked at this earlier, the extent of the basin system. So now we're going to focus on this eastern Soldiers Cap. So we have outcrop of the Soldiers Cap group and Currydale groups here on the eastern edge of Mount Isa province. So first the 07 IG1 lines. So this was originally, these basement terrains, Numal and Abingdon, were originally defined by Corsian team. And this interpretation is broadly similar. But one of the biggest differences is definition of the three distinct blocks. So Numal East has a strong west-dipping fabric and fault blocks, Numal Central east-dipping fabric and fault blocks, and distinctly lower density in the gravity modeling. Numal West has some strong reflections in it, but generally little evidence for internal faulting. Now, that's my updated interpretation, because I originally had Gidja structure, and I think there is a fault coming through to surface, but I think the fundamental boundary wraps over here, and probably the actual surface location of that structure probably projects further to the east. And that was one of the things that had been bothering me for a while, and it wasn't until we did the 3D model based on these seismic lines that I realized, yes, that probably is closer to what's really going on. Something happened there. I missed something. Oh, there we go. At least get things on there. So this is just looking now. So that's the line we looked at. Then we have CF1 going northwest through the Numal area. It's much harder to interpret. And I think fundamentally there's another more competent block that extends into here at depth. We sort of see it on the end of the M5 line, which comes pretty close to this line. But it's not as straightforward or clear as the other seismic lines. And here's CF3. We already looked at it. It swings, it's east-west, and then swings in and links up with the CF1 line at its southern end. So I've highlighted here the location where I think it was the Craton team proposed a suture when Laurentia collided. I don't agree with that because I prefer the interpretation as I flagged that numeral east here correlates with the numeral terrain that we see further south, so that things swing more in a southwesterly direction as we come to the south. And this terrain we can see down here was fundamentally here in controlling deposition of those cover basins in Mount Isa. Now I'm going to look at the basin, Soldiers Cap Group, Curry-Dalla Group Basin, but just for anybody who's not familiar, I just wanted to highlight the models, passive margin models that have developed over the last 20, 25 years, because it's quite a difference to the previous models, and some in the mineral industry are not as familiar with this. So when you thin the crust, you take an average thickness crust and you start thinning it. By the time you get to somewhere around 10 kilometers, as the stretching factor increases, upper and lower crusts become coupled and embrittled. So then your faults can extend through the entire thickness of the crust, your brittle faults, and water gets through to the mantle. You have partial hydration and serpentinization of that upper mantle that forms a detachment, a décollement, and this leads to exhumation of the mantle. It can lead to exhumation of the mantle if extension continues. That serpentinization really facilitates that. So having spent 15 years almost working on the petroleum side of things with FrogTech and looking at passive margins all around the world, when I came and I looked at this seismic line especially, I was dominantly seeing, yes, there's been a lot of shortening there, but what I'm dominantly seeing are those low angle fault blocks. And that instantly had me thinking about hyperextension. So once I spent a while thinking about that, I said, okay, well, let's try and reconstruct at least part of that basin. So that basin extends for 600 kilometers. I wasn't going to take that on. So I reconstructed this segment here of the N6 M5 line, focused on the Soldiers Cap Curry-Dalla Basin and where the Cannington deposit is located. Now, a couple of key features from the stratigraphy in this eastern area in comparison with the west. So Calvert and Isa superbasins separated by emplacement of Sabella batholith at 1680, 1670. So that's a major extensional event. And that coincides with deposition of a quartz-rich clastics here in the east, in contrast to the finer grain units above and below that. So we've got emplacement of a significant volume of high iron tholiites, and these have a morb-like composition. They're quite distinct. And the detailed mapping, I've forgotten his name, south of Cloncurry shows that these sills were emplaced sin sedimentary, so they've got those pepperite textures. Now, it's interesting, oops, there we go, because that matches exactly with what we see in the Etheridge group to the east in the Georgetown Etheridge area. We have those high iron tholiites, similar composition, similar age, intruding a package that's broadly similar. We've got the Tommy Creek block, shows some of the younger age units, and there's excellent work going on by Alex Brown, and there should be a publication coming out soon if it's not out, that provides a whole lot more geochronology and shows the extent of the bimodal magmatism, felsic, mafic, and ultramafic through to about 1615, if I remember correctly. There's another great study by Griffin et al., and they looked at the drainages. They looked at the modern day drainages east to Cloncurry. So they see a group of zircons that match the outcrop and another distinct population, 1630 to 1625. And they have a juvenile mafic signature. These authors concluded that the population was too significant, too strong, and too distant to be linked back to Tommy Creek, and suggested that there are actually younger rocks here missing from the Cloncurry area. So those rocks are either not recognized in outcrop or have just been recently eroded. So I'd argue that this package probably did include the younger rocks right up until the Eisen orogeny. So we have bimodal magmatism throughout this extensional event. And just as the Mount Isa orogeny starts, we have six garnets dated at 1605 that formed in a very high geothermal gradient. And that means we have to have heat conduction. It can't be explained by crustal thickening. And that's consistent with extension continuing until just before shortening starts. So I'd argue in the Eastern Fold Belt, at least, we had extension from 1680 to 1620, but it was probably episodic. Now, there's my reconstructed cross-section of the M6, M5 line. At first glance, looking at the depth scale, you can see I've got a central basin that's over 20 kilometers thick, and you're probably thinking, that sounds like a bit much. But my interpretation here, the crustal architecture, comes from the seismic. You can see this wedge-shaped margin to the Mount Isa crust. Then the thin low-angle fault blocks of the Numal crust, the regional detachment related to the Staveley Formation calc-silicates. And there's the Numal example. The high iron tholiites I'm showing schematically here in bright green. Now, the interpretation from Gibson and colleagues was that the crust was either breached or close to rupture based on the composition of those high iron tholiites. So my basin thickness is based on the preserved thickness. When we're looking at the seismic, we have 10 to 15 kilometers of the Soldier's Cap group preserved in the seismic. And I recognize that it has been thickened. We have that missing stratigraphy, the 1650 to 1620 age units, and metamorphic grade here at Cannington says there's been 10 to 20 kilometers of removal after metamorphism. So that's what I base it on. Now we take another step back, and what did it look like when we were depositing this middle unit that which is the key stage for Broken Hill style mineralization at Cannington, and to the east, to the west, we have the Sabella batholith being in place. So crustal thickness is not constrained. I've got no way to constrain it, but the geotherm was very high, and we have that juvenile mafic input, and we also see that in the lead source at Cannington. Obviously, heat flow in this central area is going to be too high. You're still going to have to be off on the margins in terms of prospectivity for even Broken Hill style mineralization. Now, looking at this lower section, this is my point about the low angle structures dominating during early shortening, because if this is the stage near the end of extension and just before the start of the Eisen orogeny, when you look at this crust, it is obviously going to be the low angle structures that are going to dominate as shortening starts. You're not going to form steep structures in this hot weak crust. So you're going to invert your normal faults, and then you're going to quickly end up with a room problem here. You end up with detachment forming and thrusting of a lot of this to the west over top of the Isa Craton, and then eventually the Numal crust is thrust underneath the thicker, more buoyant crust and lithosphere of the Mount Isa province. So that's my argument there. So that's just the summary chart, the difference between the lead isotopes for Century, HYC, Mount Isa, in contrast to Cannington, Pegmont, and Broken Hill, which are more juvenile, as opposed to the more evolved response here. This is an image from that paper, Griffin et al. That I mentioned, and you can see this increased juvenile input highlighted in blue, and that juvenile input peaks during the Soldiers Cap group, Curry-Dullah group time. So going to the tomography model, I brought in that cross section, and it's it's a big regional section. And when I sort of try and indicate about where that seismic line sits, you can see it's just tiny in there, but you can see it sits there over at the edge of that thick protonic lithosphere in the transition into the thinner lower velocity lithosphere. And the interpretation that the cratonic erosion was related to rifting, I would agree with. With this level of hyperextension, you are going to thin and significantly thin and remove your subcontinental lithospheric mantle. So thinking then to Mount Isa, and you can see where it sits here in the west over this thick, buoyant crust and lithosphere. It's relatively competent because it's been extensively intruded. In contrast to Cannington to the east. And so this line we're looking at CF3 well to the south, and this is the 94 line that sits just south of Mount Isa. So you can see that Mount Isa would sit adjacent to the Mount Isa fault, which would be a second or third order structure related to that terrain boundary. In contrast, looking at Cannington and Pegmont, we have the much thinner crust dominated by the faults and low angle fabric, evidence for the juvenile input. So that the Cannington and Mount Isa differ at least in part due to the tectonic setting and the fact that we had a hyperextension here in the east. Whether we ever get to the point that we exhumed mantle or even that we had oceanic spreading, it is unclear. We may have just gotten to the point of very highly thin crust, but we clearly see that juvenile input. And this gives you an explanation for the high metamorphic grade that we see at Cannington in contrast to lower metamorphic grade to the west at Mount Isa. I'm sure I had another point here, but I've forgotten what I wanted to follow on with there. Just let me see where we go to next. Okay. Just to wrap up, so we have the narrow rifts within that vast basin. We have the narrow rifts north-south, east-west, north-south here. In contrast, we have that broad rift over the hyperextended crust in the east. Okay, quickly coming in here to the Tennant Creek area, Western Queensland, and then Tennant Creek. So I'm just checking my time. So we have a broad area of cover between Tennant Creek and Mount Isa, sort of 500 kilometers. We have oak crop here, some reasonable oak crop around Tennant Creek, but there are some similar age units that we see just on the edge of the Mount Isa oak crop. Camarga basalts and granites here, west of Mount Isa, and a few units here in the south. With the EFTF work and the drilling, GA put together, done a lot of dating and work on that, and we see we have equivalent rocks in that area, the Warramunga equivalents and the granites. So we've got a lot of prospective territory, although we have thick cover, and we have to think about where that cover is thinnest. So there's a lot of detail in here, but the key thoughts I want to highlight here is the Davenport event is not well constrained. A lot of workers will argue that it's younger, and that the Tompkinson Creek and Hatches Creek units, which are strongly folded, are equivalent to Tuala. Red Bank, and which is equivalent to the Leichhardt Superbasin. So you would have to argue that that folding is localized and doesn't extend up into these large outcropping areas, and that's possible. But there's evidence in the southern edge of Mount Isa where the Jaya Creek basalt, which some people would have equivalent to the Eastern Creek volcanics, but it has to be older because it's intruded by a deformed 1782 granite. Whereas all the sediments interbedded with that Hazelington group have tridal zircons from 1768 to 1780 dominantly, and a little bit older. So clearly those units are younger, and with that deformation through here, my current interpretation would be that the Davenport event is a bit older and Tompkinson Creek is older. So you can see the outcropping units, Orodigi and Warramunga from the Tennant Creek area, the new GA data highlighting Alroy and the intrusions here. I'm going to focus on this area from the seismic. There's the Coangela seismic package that I think is broadly equivalent to these units and gives you an even more extensive area of prospective rocks. And that's key because these are the units that host a lot of the gold at Tennant Creek and west to Tanami. So just to show you where we are, here's Mount Isa in here. So we're looking at a set, again, of 9 shorter seismic lines here just in the Western Queensland area. This was a GSQ project, so we're focused on the Queensland side, but we'll then look into the Northern Territory. So again, this interpretation is focused on basement, and we've defined 3 main basement terrains through here: Murphy South, Tennant, and then Altuara. But it includes a first pass interpretation of the cover basins to help us understand the basement. So we have outcrop of Isa here in the north on the old M1, M2 lines, and a bit here in the south. But as we come further south, we just have Calvert at surface. And then through much of this area, we've got a thin Georgina sitting over top. And so Nicholson and Basin interpreted from the seismic, but it is absent here in the Carrara 1 well that sits in here. I think, oh, yes, I knew there was one more point here. This area, so this Calvert I'm showing extends down to about 7 seconds two-way time, which says you're getting up towards 20 kilometers of your total basin there, which sounds a bit extreme. But given the undeformed nature, given the nice growth package that we're seeing here into the Carrara Fault, that's the biggest thing that sways me towards having this as a cover basin rather than part of the actual older Tennant package that then, because this package has been more extensively folded during the late deformation. But this package certainly could include Calvert as well as Leichhardt and maybe even some older units. The Babak Hadrani last week at the EFTF presentations showed a slice from a 3D velocity model that he's created from the passive seismic. And it does show that there is a velocity contrast somewhere near this transition between the blue and the orange. But we do have evidence from the gravity modeling. It's consistent with the gravity modeling that there is some higher density units in there that may well be volcanics. So looking at this, you can see the limited depth extent. There's the 3D image and then just stretched out as a 2D image, that this Tennant Basin terrain is limited depth extent with quite a thick package of supercrustal rocks, including the Warramunga, Orodigi, Tompkinson, and Hatches Creek groups. And they overlie a basement which models as higher density, some low angle fault blocks. So with this divergent geometry, I see this as forming during due to extension, and so that the Tennant terrain that we see at surface when we're looking at it, those boundaries, is dominantly a rift that accommodated the 1870 to 1790 package, and that this underlying basement is reworked basement from the Murphy South and the Altuara basement terrains. So there's the density values on top. So Murphy South is consistently about 2.81. This block, 2.8. This block comes in at about 2.81. We have a strong basal reflective zone, 2.9. Altuara sits at about 2.79, tends to typically be just slightly different density to Murphy South, whereas this overlying package is got a density of about 2.75. Now, looking from the outcrop maps, I'm just checking my time. I don't want to go into too much detail here. So this is from the Monash group, and summarizing, just subdivided the main age packages. So the ones we're interested in here are in orange, sort of less than 1900 to 1850, and then in yellow. And so we can see here in the Tennant area, we have, so within, we can extend through to the Tennant area and then to the north, providing a much wider range. So we'll just look at that in a bit more detail on here. So this is from CAB's presentation, and there is a conference volume that I understand is in press. The conference was last August, so I expect it'll be out soon. So this is a composite that goes from the Beeloo Basin across the Murphy Basement High and down to the Carrara Subbasin here. We can see the rift package. Now, I've flagged here because Calvert on this is now a bright green, and the young South Nicholson age package is in purple. We're just trying to get those distinct colors to help highlight. So you can see the rift growth package in both the Isa and the Calvert, either side of this granitic basement high. And that was another thing that Babbitt flagged from the passive seismic data, because this is a big gravity low, and people have debated whether it's a basin or a granite, but there is a velocity contrast between this zone and the areas to the east and west. So I am more confident with that. And here's the distinct Coangula seismic package. So this is quite thick, and you can see the repetitive nature of it. It's very similar on this SNN composite line that is highlighted here in red. It's more north-south, but you can see that package. And so it looks like with those strong, bright reflectors, it looks like you've got mixed volcanics interlayered with sediments. So we have the fairly uniform red bank package sitting on top, and based on outcrop, it looks like the Westmoreland conglomerate comes through here, and it looks like we've got an angular unconformity with the underlying Coangula package. And in turn, that looks like it's intruded by the Nicholson granite, which outcrops just to the east of this line. Again, we see some really nice growth packages especially in the Isa superbasin through here, in contrast to the broader subbasin in the Carrara subbasin. So the deposition, both the deposition and the deformation, and the inversion of that Isa superbasin is very localized within this brunette rift corridor, and that coincides with that Murphy South terrain. So I think there's quite a clear control there. So this is that composite line we were just looking at. So SN5 comes up to here, but we've got quite a dog leg here going to the other seismic lines. So this image is just SN5 right to the end. So showing it here. So coming down just on that north-south line. And I've squished it up so it's at the same one-to-one scale here in the south, and then showing those units over the basement terrains. So we can see we've got the more uniform red bank here overlying Coangula. the Brunette Downs Rift Corridor overlying the Murphy terrain, which we interpret as an accreted arc. So when we started in plan view with the gravity data, you can see there's a distinct low density zone, which is equivalent with the Murphy North terrain, and it's bounded by this high density zone, the Murphy South terrain. So that highest density here is right at that northern edge. So that's probably a high metamorphic grade accretion complex, and then the accreted terrain to the south. And just highlighting there the Murphy South terrain thrust over the thin margin of the Arnhem terrain. Now you can really clearly see the difference in the nature of the cover basins overlying Murphy South in comparison to those overlying the Arnhem Craton. So we have the more uniform red bank package, and in fact, this the main Isa package is not deposited over this Arnhem Craton. There is just a thin upper unit that is equivalent to the far bank in the NT. So looking at this, I thought we've got the Coangula and then the Tennant units. Were these ever deposited on top of the Murphy South? Possibly, but if they were deposited, they've probably been eroded, because if this is forming as a rift, then we'll have footwell uplift of this basement here and non-deposition, although this onlap may have come over a bit in the north. So looking then at these units, which are key host rocks for gold deposits, we now know they extend here. So that's the East Tennant area and all the new data from GA. Then looking at the extent on the seismic lines I've showed you here in the Tennant rift, and then extending north here, the Coangula seismic package. Now, looking at the gravity data, there's the extent of the Coangula seismic package. And one of the features of the gravity that has always bothered me, and I've been looking at this data for over 15 years, is the fact that even when you have high resolution gravity data, these gravity anomalies are quite broad and subdued through this area. Now, we do have some near surface effects related to the thicker basins here in the Beetaloo Basin, but wherever we're seeing from the basement is just broad subdued anomalies. And then Lynn Pryor was the one who said, well, maybe that's just showing you the extent of the Coangula package, which is sort of thickest through here, but probably extends through here. So although we've got this mixed sedimentary volcanic package, which will vary a little bit in thickness, it is broadly uniform. So it's providing a blanket that is giving us a masked response to the underlying basement. Now, there we go, wrapping up. Looking back to the Pine Creek and Arnhem Cratons, we see here in the north, we have a clear relationship between the basement terrains and the depositional history. We see very distinct variations in the basin stratigraphy when we look in detail through here, and there's a bit more detail in the CABS paper. And that's controlled by the rheology of the underlying basement and its mechanical response to the tectonic events. So together, these factors control the rate of subsidence and geometry of each stratigraphic succession, as well as their subsequent preservation throughout a number of deformation events. So this is key because you can really get predictive. If you can understand this, you go to the covered areas and you can be really predictive on those depot centers, which are key host rocks. So the start, this all began with the identification of the basement terrains and those major boundaries. Now, Mount Isa versus Cannington, pardon me, we have the thick buoyant crust, a clear cratonic lithosphere beneath Mount Isa, with smaller rifts that are probably linked to those terrain boundaries and the deposits forming on second or third order structures, and probably similar at MacArthur River. Further east in Cannington, we have the low angle fault blocks, and we're overlying that sharp transition in the subcontinental lithospheric mantle. And that may it will dominantly relate to thickness, but there may be a composition factor in there as well. And we see that clear juvenile input. So that fundamental difference in the underlying crust and lithospheres control the basin evolution, as well as probably the location and style of the mineralization in terms of Cannington versus Mount Isa style. Now, coming back to the simplified cross-section from Hoggard and others, I don't disagree with this. I think they've got quite a nice explanation, but that the significance of this step in the lab may just be a step. It doesn't have to be the cratonic margin. It may just be a step. And we see that projecting Mount Isa sort of 50 kilometers onto this line, which sits at about 20 degrees. So, and you can see we do have a step in the cratonic lithosphere there. HYC sits 400 kilometers north, so we're not getting a good look at it, but from plan view, it looks like we've got a step there as well. So we are seeing this model, but I think this difference, although it may be a subtle difference, I think it is key because it's significant to target generation. So if you're looking in plan view and really focused on those margins, you may be missing those more subtle steps in the lithospheric boundary. So where you've got the tomography, you can work with that much more clearly. If you don't, starting from the top down, you can think more about your terrain interpretation, look at your moho depth and variations in basement thickness. Okay, so just back through our cross-section across the North Australian Craton, from our low Newmel and Abington, dominated by the low-angle fault blocks, to our thicker, buoyant, more cratonized crust across Mount Isa, and then swinging north to look at the Tennant Rift between the Murphy South and Altuara terrains, and then stepping west to look at the margin, the boundary between the Murphy South, where it's thrust over the thinned margin of the Arnhem Craton. And again, this section that I've extrapolated to the west where we see that Malapanya. The gravity in the data is not as clear as we come south towards the Batten fault zone in comparison to the Walker further north. And we have a dog leg here as we're just stepping through that. So we're not getting a clear understanding of that. And I think we're part of the signature is obliterated by that thick coangula package over top. The two cratons, cratonic blocks beneath the Beetaloo Basin, I think, have provided a stable zone where you've had more uniform deposition, but there is that central arch that stands out in the gravity data and looks like a narrow orogenic belt. So if we can understand the crustal architecture, we can go a long way with that. So in plan view, to finish up back to our map here, if you spend the time trying to unravel the basement terrains and crustal architecture, you can get some really significant insights on the tectonic evolution, on the distribution and thickness of your cover sequences that may be prospective, as well as your, clearly your first order fluid conduits related to those terrain boundaries and their links to the second and third order mineralized structures. So start with the gravity and magnetic data. Just pull them out and work with them. And if you've got the other data sets, they obviously can provide a lot of information. But if you haven't got them, I wouldn't let that stop you to try and do this sort of analysis. So thank you very much. I've tried to get a summary of most of the references. the work around Mount Isa and Newmore. There was a short report I did originally, but the main seismic interpretation was published in late 2021 by the GSQ. There must be a dozen conferences where most of the presentations are available online. The NT Queensland border, there's the AGES abstract and presentation, and Janelle and Dom and I have another report on that area that's in the publication queue. And as I mentioned, there's the CABS short paper and abstract. I'm not sure whether the presentation was made available. And I did just want to highlight there is the Digital Earth project that the SMI group at UQ are working with Euclidean and GSQ to develop a digital Earth model in 3D for Queensland. So if you're interested in that, Steve has been presenting on that, and that's just a 3D image of those seismic logs, showing the Numal and Pita terrains. But this has got they've been very focused on getting the drill hole data and the near surface data in, but this the larger scale crustal data is currently coming in as well. So thank you.